Okay, so I'm going to do a second graph set in here on Logger Pro, and I'm going to put in inverse volume units m to the power of -3, and I'll put that there. And then on the Ry, we're going to still keep it with pressure. Now, what I'm going to then say here, pressure as well, measured in pascals. Now, again, our pressure, we might have a fixed value. So I'm just going to give us some really easy values here. So like 1, 2, 3, 4, 5, 6, 7, something along those lines that I can just like write in. And again, I'm maybe just going to have here, my inverse volume is what, so 0.5, 1, 1.5, 2, 2.4, 3, 3.4. So like some values in. These are not realistic values, they're just some examples that we're going to kind of just see for plotting our graphs, okay? I'm going to go into pressure and I'm going to just add in a fixed error value because we've got our pressure from before. So let me say 0.5 or 0.01 or 0.1. Let's just put that in at 0.1. And our x value, we're going to add a second column in. So I'm going to go to data, I'm going to add a new manual column. I'm going to call this the uncertainty of inverse volume. Okay, so in this case, I'm going to add in, let's say I'm going to do them as a percentage, so I'll say this one was 2%, this was 3%, 5%, maybe this was, again, a 4%, a 5%, 6%, and a 3%. Now, what I then do is I go to X, I go to error bar calculations, I'm going to click percentage and use column, and I'm going to say uncertainty of inverse, okay? And what I'll do there is click that in, and I've got my error bar values. So, we're going to upload this, and we can see that we've got these error bars kind of looking through. I'm just going to actually just make my pressure a little bit larger, just for sort of showing you how to do this today. Now, what I want you to imagine is each of these error bars is forming a box, okay, around. So if we kind of imagine here, this all forms a box out, which essentially tells me that this data point could be anywhere within this box. So the first thing we're going to do is just put our typical trend line in, and I'm going to put my trend line just over on the side. And now I'm going to take my, I'm going to do my max line of best fit. Okay, so we're going to take our values, and I'm going to go to add fit, and I'm going to go to manual, and I'm going to go to linear, and I'm going to say okay. Now this manual fit, we're going to click on appearance. I'm going to change it to a color so I can differentiate it between the first one. So let's say I'm just going to use cornflower, and then I'm going to say use enable line drag and use the entire range. So enabling line drag allows me to now manually move this. So I'm going to try and take it and put it through what would be like the bottom of this box and going through what would be like the top of this box over there. Now, I'm going to leave it kind of here for the where I sort of like, I'm estimating it by eye at the moment. And I'm going to take enable line drag off because I'm going to now add in another line. So again, I'm going to highlight my area of which I want this line to go. I go up to manual fit. I go to manual, linear, and I'm going to again say okay. This time round, I want to double click on it again. I'm going to change the color. Let's go up. Let's say this time I'm going to use dark orange. Enable line drag and use entire range. And again, I'm just going to click off that yellow so I can see it better. I'm going to put in this max line. So again, taking it up to the top, bringing this one down. And again, I want it to be going through as many of these as possible. Ideally, it should pass through them all. The other thing that we want to have is we want these 3 lines to intersect at the same point. So this sometimes is a little bit tricky, because what I'm going to have to do is play around with these little lines together. So I can sort of see I'm coming off that a bit too much there, so I want to lift that back up. they are kind of intersecting, but maybe not fully as clear. So if I try lifting that up a little bit, that's going a little bit more off. So I'm going to leave that one and go back to enable line drag and tick it off. That's my max line, so I'm just going to move this up, move this down, just so I've got them in order, so maximum gradients at the top. I'm going to go back to my purple one, enable line drag, and maybe I'm just going to play around with this just a little bit more, just to sort of get this intersecting at the one point. And again, because I don't want to see these diamonds, I take the enable line drag off, and I can have all my 3 gradients on there. So now I've got my maximum gradient, my average gradient, and my minimum gradient. Okay, so I've got those. I'm going to take each of these and I'm going to place them into my document. Okay, so I'm going to go back over here. So maybe what we then want is we've got like a gradient, so I'm going to read this off the trend line. What I could also then do is I could put in a box and say max gradient, and then I could also put in another one saying the minimum gradient. And again, from the trend line, we can see that my gradient, so my line of best fit, is 2.056. So 2.056. Oops. Need to place that up there. Oh dear, it's all going a little bit wrong on my typing today. I'm going to read off my minimum gradient and my maximum gradient. So again, coming back to this, and this is why I like to put them in my order, so I can see this is the steepest and this is the least steep. So this is my maximum, 2.377, and then 1.711. So 2.377 and 1.711. Let me just double check that. Yes. Okay. So I'm writing in kind of the equational calculation here. At this point, this can let me now do my mean gradient. So my mean gradient, so I've got my gradient that I've taken off just like the normal trend line, but I can also calculate the mean gradient, which is going to be my maximum gradient plus my minimum gradient over 2. So we're taking the mean of these 2 values here. So again, you could do this as a table, you can set up your calculations in a different way, just put all mine together for ease. Again, max plus minimum gradient divided by 2. The other thing that also having these minimum and maximum lines here, first of all, it can also let me talk about the y-intercept a little bit and where it crosses through. But it also now gives me an uncertainty of this gradient. And the easiest way we can do is simply to, again, just like we did with when we got multiple trials, we're just going to take our range and divide it by 2. So if we go back, our uncertainty of our gradient is maximum gradient, take away the minimum gradient and divide that by 2 there. So again, if we're going to do that, that's going to give us now our gradient and an uncertainty of our gradient. Now, why am I taking those gradients? Well, I'm using this to find out my number of moles, because from the ideal gas law equation, we know that PV equals nRT, or P is equal to nRT times 1 over V, which is really into the format of y, let me just start that again, y is equal to mx, where nRT is our gradient here. So our gradient of our graph is the number of moles times the molar gas constant times temperature. So number of moles, if I rearrange this, just becomes the gradient divided by RT. Please be careful, your temperature should be in Kelvin, all right? You probably took them on the day in terms of degrees Celsius. So again, you can calculate your number of moles. But since we have an uncertainty of our gradient, we actually have an uncertainty of our number of moles. And because we're doing a division here, we're going to have to add the fractional uncertainty to find them. Remember the rules, if we multiply or divide, we add the fractional uncertainty. So in this case, I'm going to take the uncertainty of n divided by n. Let me just make that a little bit larger. The uncertainty of n over n is equal to the uncertainty of the gradient plus the uncertainty of temperature over temperature. R is a constant, so it has no uncertainty, so I don't need to add that into it. So again, with this, our uncertainty of our gradient divided by our gradient, And then temperature you should have recorded, and you should have an uncertainty with that temperature as well. I think most of us were using a digital scale. So remember, how do we take uncertainties off digital readings? That can give me the fractional uncertainty. Again, you could turn that into a percentage, or if you wanted, you can then convert this back into a numeric value, and so you've got an absolute uncertainty there. And in this case, we're just going to take our delta n. Remember, that's just absolute uncertainty of n. We're just going to take that fractional uncertainty that we calculated before and multiply it by our number of moles that we have. And that will give us our absolute uncertainty of number of moles here. So in this case, I'm going to have number of moles, the fractional uncertainty of them, and then the uncertainty of them. So I've got little kind of values here that I can discuss later. So just a kind of little examples of how maybe you want to lay things out. Again, like we had a bit of problems in our last lab, if you're doing calculations for graphs, I need to see the graphs first. So your calculations of the graphs should come after your graph. And for example, your calculations for your data table should be with your data table. So just think about your formatting, your presentation of where these should all be. Okay, if you have any questions, please let me know. And that is it.